Hello and welcome everybody to this week's seminar. My name is Homero Larrain and I'm going to talk about express service design on a bus transit network. First of all, let's take a look at what a regular service is. A regular service is a bus service that stops in every stop along the route, while an express service is a service that serves just a subset of the stops on the route. Naturally, some of the users will be specifically happier with express service than other ones. In terms of travel time, express services will benefit some users and some other users will be left just the same. In terms of waiting time, some users are going to face longer waits than before if we implement express services where some regular services were operating and sharing now the fleet with some express services. In terms of transfers, express services may force some users to make some transfers if we stop giving regular operation and we replace it with a set of express services. And in terms of operation costs, express services usually mean cheaper costs for the operators due to short cycle times. Express services are currently being used in many parts of the world. 38 different countries have this type of systems, and 158 cities in these countries are using them on 280 different corridors. There are some studies on the topic of express services. Some of them are case studies or oriented as case studies, such as the ones I'm showing you here. Some other of them, which ones are the ones we're more interested, are the ones that try to solve the express service design problem. These works are summarized here. As you can see, the first one is the one of Jordan and Turnquist, and it deals with the problem of optimizing the frequencies of different services and generating these services. The model generates its own services, but it doesn't work with a flexible demand matrix where you can go from anywhere you want to anywhere you want. Instead of that, they assume that all the demand is going to the same final destination to make the problem easier to solve. Following works in the last years deal with a real OD metrics and deal with optimizing frequency of the services, but they have different features. Some of them are still able to generate their own services, but don't deal with other issues. The first one, Sun et al., doesn't deal with the issue of common lines. That means that when a user has the option to take the express services or the regular service to get to the destination, they will usually minimize their respective travel time. Sometimes they will take the first service that gets to the stop, and sometimes they will wait to the express service to get to their destination even faster. And this model doesn't take that into account. Leiva's model, Leiva, by the way, is a student of Juan Carlos Muñoz, the same as I. Leiva didn't work with service generation directly. They made a model that takes into account many of the other issues, but the modeler has to feed the model with a set of services, with a set of express services. So it's not exactly a generation model, an express service design model per se. Some other works, such as Ten et al. And Tirapankan, sorry, and et al. Work with the problem of common lines. They also deal with capacity in a sense that their solution has, their buses have enough capacity to take all the passengers where they want to go, but they violate user equilibrium when they are dealing with capacity, because they impose capacity as a restriction to a social cost optimization problem. And as we will see further on, this might generate situations where user equilibrium is not satisfied. Of course, we're going to try to deal and tackle all these issues in one single model, and furthermore, we want to make a model that's able to work on a network. None of the models we're showing here work on networks. They are all models for isolated corridors. So what's the deal with capacity and user equilibrium? When capacity levels are not reached, we can safely assume that the optimization, when you optimize social cost, we will get to a user equilibrium, because every user can do whatever they want, because they can share capacity. Capacity is enough for them all. But when capacity is taken into account, the results may not be consistent with user equilibrium, because they have to compete for capacity. So we developed an iterative method where frequencies are increased until we meet requirements without making users fight for their space on their buses. And the solution obtained by this method satisfies capacity constraint and user behavior. I'm going to show you a little example later of this. So the main question of our research, of my PhD research, was how to design express services. More specifically, we were looking for a method that could generate its own services, that would reach user equilibrium while minimizing social costs, that don't exceed bus capacity in its solutions, and that would work on public transit networks, not just on isolated corridors. So our methodology, an overview of our methodology, would be as follows. First of all, we have to create a module that would tackle the service generation problem, that would generate different express services that would be reasonable to consider for the solution of our problem, and we will feed these services to a frequency optimization problem similar to the one that Leiva already developed. So these two modules can iterate and interact between each other to solve the problem, at least on an isolated corridor. Then we want to use this model that can solve the problem for a corridor to solve the problem on a network. And we can generate a feedback between the network and the corridors to look for a solution for the whole network. On the rest of this presentation, we will face three main topics. First, we will talk about service generation. Then we will talk about frequency optimization. And finally, we will talk about express service design on a whole network. So let's start with frequency optimization. As I told you before, the frequency optimization problem was already tackled by Leiva on her master's degree thesis. And it basically takes a set of lines such as the ones I'm showing you here. They can be different lines. We have F1, for instance, that's the regular service, and the rest of the services that serve different sets of stops along their ways. We can even take some services that don't serve the whole corridor. They are kind of short-turning services. or even like FN, that they are short-turning and express services at the same time. They don't cover the whole length of the corridor, and they don't serve every stop along the route. The Leibas model worked on this objective function, and the meaning of each term is the one that I'm going to show you here. First of all, we have the operating costs plus waiting cost of the users plus in-vehicle travel time cost of users and transfer cost of users. This is a social cost function, and we're going to try to minimize it. This function will be restrained to sign restrictions. Of course, we want every frequency to be positive, and of course every passenger flow to be positive as well. We're going to make sure that the flows are continuous, because we're working with transfers, and we're also going to impose a new feature of the model that I had to add to be able to use it to design services. That is the continuity of frequency. That means that the sum of the frequencies that finish the service on a node has to be the same as the sum of the services that leave that node, that stop. This model will give positive frequency to attractive services. It will not necessarily use every service you feed to it. The model is useful. It may leave some of the services out, so it can help us to choose which services to use. How will we deal with capacity, or capacity heuristic? It's really simple, actually. Let's assume that we have an initial solution like the one you're seeing here. We are giving frequencies to the first 3 services. We're going to use just the first 3 services, and let's assume that the second one has a load of 120 passengers per hour on the critical arc, but that our bus's capacity is of 100 passengers per hour. We're going to add a new restriction where we force the frequency of that particular line to be increased, and iterate until we reach a feasible solution. But our solution is not going to be optimal, because our initial solution is optimal, but when we add these frequency restrictions, we're going to get to a solution that is feasible, but it's not really necessarily optimal. It's hopefully near optimal, and the tests we have made show that the model is still able to find good express services solutions. The other problem is that it has to solve the optimization problem in every iteration. But we saw that we can adjust that delta step to a more smart state, to bigger steps that will lead us to an equilibrium, a feasible solution in less iterations. That's one of the improvements we've made to this model. So that's all about frequency optimization. Let's talk about service generation. In my PhD thesis, I present many heuristics for this problem. Some of them work starting with a regular service and then taking out some stops that are promising as skippable stops based on some indicators we developed. We also developed an inverse approach where you start with an express service that go from the first stop to the last stop, and then we start adding the stops that generates more benefits. We also have some heuristics that work on particular configurations such as short-turning and zonal service generation. We will show you later on detail what is zonal service generation about. We also have some heuristics such as short-turning, zonal service, and mixed service generation for congested scenarios. We mean scenarios where we know that capacity is going to be binding. When capacity is binding, you can identify the critical arc, and you can say that frequency has to be at least the minimal frequency to serve those critical arcs, and we're going to use that to solve the problem to optimality. We will show you an example of that. So when we talk about service generation, zonal services are going to be defined as follows. First of all, we're showing you here a regular service, FA, and an express service, FE, that is zonal in its configuration. It means that it serves a set of stops at the start of its route, then it skips a set of consecutive stops, and then it serves a final set of consecutive stops. If we want to optimize the frequency of the zonal service, we have to identify the different types of users that will use this system. First of all, we have the users that are directly benefited by the express services, the users that hop on the first segment of the express zonal service and go to the final zone of the service. They are going to be benefiting from the time savings on the skipped stops. Then we have the users whose services are contained in any of the initial or final zones, and they are not going to be really affected by this measure. They are going to just face the total frequency as the frequency of their attractive frequency. And finally, we have the rest of the users that are going to be affected by the eventual decrease of service of the regular service. The diminishing of the frequency of the zonal service is going to affect them. So taking this into account, we can construct a social cost function, assuming that we know how many passengers are going to be affected by this measure, but this number of passengers does not depend on the frequencies. It depends only on which is going to be the zonal service. So we can choose a zonal service, compute this total number of users, and then we can evaluate the social cost function in terms of FA and FE and optimize it for these frequencies. And that's what we did. We're going to skip how we get to the optimals. We're going to just mention that we can also compute the regular service optimal social costs. We know that if we only use a regular service, we can optimize its frequency, and we can know what are going to be its optimal costs, so we can tell if it's good to use a particular zonal service or it's not. So the zonal service generation heuristic for the uncongested case is basically evaluating every possible zonal service. There's no that many zonal services to evaluate, so it's not really a problem. Compute the social cost for the express service scenario and the only regular service scenario and compare them. And if the express service yields benefits, then we're going to feed it to the frequency optimization model. We're going to use this method to find a set of services that we can feed to the model. And as I showed you before, we have a number of different heuristics that they all are able to design the services. So we're going to use it to find an initial set of services we can feed to Leiva's model. If we take capacity into account, sorry for this slip, there's a little Spanish there. We have that the total frequency of the services we give has to be at last enough to carry all the load on the critical arc. And this can lead us to an optimal social cost to the optimal frequencies of the model. We're not going to get into it here. You can take a look at my PhD thesis. It's going to be published in a couple of weeks. And if you don't speak Spanish, you can be a little more patient and wait for a couple of months for us to publish these results in details. But we can use this analysis to find optimal frequencies for the restricted, capacity restricted case. And this is good news because it means we can find optimal solutions for congested scenarios. remember that on the first part of the model, we dealt with capacity with an heuristic that led us to solutions that were near optimal but suboptimal anyway. So this is good news because we can develop some methods that for a limited set of services can lead us to optimal solutions, and this opens new lines of research that we think are really interesting. So this is an example of a test we did on the last two heuristics. Let me show you what it means. First of all, we generated one basic scenario without congestion, without express services, and a second scenario where we designed zonal services using our heuristic and fed them to the frequency optimization model. This is scenario 2 in this table. On the other hand, we have the congested scenarios. We mean the scenarios where capacity is binding, and we also have the base case scenario, but we had to fix its capacity. And we used the heuristic we showed before, but it's also possible to solve it analytically, and it leads to the same solution when you work with only one service. We also have scenario 4 where we work with zonal services, but we feed the zonal services of stage 2 to the model, solve it, and then adjust the frequencies using the capacity heuristic I showed you before. Finally, we solve the problem using the zonal algorithms with capacity, the last one we showed you. On the right side of the table, you can see that the number 160 is painted on red, and that's because that's the capacity we assume for the system, for the buses of the system, and it's binding. You can compare that solution of scenario 3 with the one on scenario 1, where the maximum load it's clearly exceeded because we have a bus that carries 273 passengers there, as you can see. So what can we say about our results? First of all, we can say that, and sorry for the Spanish here again, that the reduction in social costs for the two last heuristic, the ones with capacity, are around 10%. And furthermore, than our zonal optimal solution was better than the zonal solution with capacity heuristic. This will not happen every time, because the zonal heuristic with capacity heuristics start on a bigger set of services that can lead us to different solutions. It explores a bigger domain of the problem in simpler terms. But anyway, we're showing here that the zonal service design heuristic with capacity can beat the other options we were working with before. And finally, I would like to point out that the solution we reached in scenario 5 could have been reached in scenario 4, but it wasn't. Scenario 4 started with every service we used in scenario 5, but the iterations led us to a different solution. So the combination of these two heuristics or these two modules give us a method to solve the express service design problem on a corridor. Now I'm going to show you how we can use this corridor tool to solve a network problem. So first of all, what's the difference of working over a network? On the frequency optimization problem, good news, the problem is just a problem of scale. You just have to deal with more nodes, more variables, but the nature of the problem is the same, and you can use the same Leyva's adapted model to solve it. The only thing is that you have to somehow generate services for a whole network, and it's even more difficult than before. You have to rely on the good sense, on the common sense of the modeler to feed the model with good services, and that's exactly a problem. The service generation problem doesn't work anymore, and our methods, the one that we showed you here, can only work for a corridor. So we're going to have to adapt the problem somehow. Our idea, or the basic idea, is that we're going to apply service generation over routes, over isolated corridors, and then optimize the frequencies for the whole network. And we're going to iterate. We're going to focus on a corridor, optimize its routes, and then optimize the frequencies for the whole network, and then focus on a different corridor, on a different route. We're going to call them route because these are not physical isolated corridors. They are just possible trajectories the buses could follow on the network. So another overview of the algorithm is the same thing I just told you. First, we're going to choose an initial set of attractive routes for the network. By route, we mean possible routes the buses can follow. We're not talking about the stops itself. So we can design express services over these routes. Then we're going to optimize the frequencies, ignoring congestion, of the initial solution where every route is served by a regular service. And then, while certain convergence criteria is not met, we're going to say that for every route, we isolate the demand for the services contained on this route, and then we generate new services for this resulting corridor. We take the current demand of a route and we redesign the services on this route using the heuristic we already showed you. And then, taking these new services and the existing services for the rest of the network, we're going to re-optimize the whole network. We can iterate doing this until we meet certain convergence criteria. Finally, when we have some convergence, we're going to deal with capacity using an adapted version of the capacity algorithm we showed you before. So let's work on an example to make it more clear. Let's assume we have a simple network as the one I'm showing you here, just 15 nodes, and one node in particular, node 5, where people can make transfer between different routes. And let's define the routes on this network. First, we will have route 1, the one that goes from 1 to 10, route 2, the one from 1 to 15, and route 3, the one from 10 to 15. These routes are designed in a bidirectional way. Route 1 will include services that go from 1 to 10 and services that go from 10 to 1, and of course services that are contained along the route as well. How can we find routes for a network? This case was very straightforward. We had just these three options, but in a more realistic scenario, we can have some problems finding our networks. But our idea is that you can just use the existing regular services as routes to solve the problem. Or, alternatively, you can use a route design model like the ones you use to design the regular services. Before we get to the algorithm, we're going to show the performance indicators we're going to use to compare the solutions to measure the benefits of the scenarios. So first of all, we have OC, that will mean operator costs, TTC, total in-vehicle travel costs, WTC, total waiting time cost, TRC, total transfer cost. Notice that these are the four parts of the objective cost of our model. These are the four components of the social cost. The user cost is going to be defined as the sum of the three last components, and the social cost is defined as the sum of every component before. The social cost is our objective function. Then we have FTTC, defined as fixed in-vehicle travel time cost. And this comes from noticing that when you measure total travel time cost, you are taking into account a big chunk of fixed travel time cost that you're not going to be able to solve by skipping bus stops. The only savable travel times that you can get are the ones due to stopping on the stops, or sometimes taking shortcuts. But we're not going to deal with shortcuts, at least not directly in this example. We can adapt our model for that. So we have this fixed in-vehicle travel time cost that is equivalent to think of what's the time if every passenger was able to ride and express services from their origin to their destinies. That time is going to be fixed. There's no way we can save that travel time cost. So we define a correct social cost function that takes the social cost and subtracts the fixed part of the travel time cost. This was done to make the reductions more perceivable and easier to compare, and also because many other works in the literature take as social cost, as their social cost, the maximization of cost reduction, and that's equivalent. That's the same as working with corrected social cost. So to make our work comparable to those other works, we're going to work with this corrected social costs. So let's find an initial solution for this network. That's going to be done by defining express services for every route and optimizing them with the Leibas adapted model we showed before. So the results are the ones we're seeing here. We have 6 lines on the table on the left. These 6 lines correspond to the 2 regular service on each direction of each one of the 3 corridors, of each one of the 3 routes, and the corresponding frequencies and maximal loads. Then we can see the different indicators of this solution, but the interesting part is going to be analyzing how they evolve, not their initial values. So let's skip to service generation, the first iteration of our model. First of all, we're going to isolate route 1. Route demand is confirmed by trips or trip stages assigned to services that are completely contained by the route. We're going to look up on our services which services are completely contained by our route, and then we're going to take a look at which passengers are using them, even for trip stages. And then we're going to redesign the services on this route to better suit the demand it is facing. We also have to be careful because some other services on the rest of the network interact with our services on the stops, because when a service ends its service on a stop, it can start giving service on a for one different corridor. So we have to ensure that the frequencies on every node satisfy continuity. So we're going to add to continuity restrictions an exogenous frequency for the services of the rest of the corridor. In this case, we will have to force the model, for instance, on node 1 to make sure that the service that went from node 1 to 15 and the service that went from node 15 to 1 to be taken into account on the continuity restriction for node 1. The results of this stage are as follows. First of all, we have to point out that the service generation algorithm added 3 new services to our solution with the frequencies we're showing there. Those are new services. And we're starting to see some savings. This corridor yielded savings of around 8%, a similar magnitude to the ones we saw before that were around 10% on the service generation examples. But we have to point out that the solution we're getting here is not a user equilibrium, because we're reassigning trips on this particular corridor, but we're not giving the users of the rest of the network the option to move the trips to this corridor if it was attractive. So when we look at the whole network, equilibrium is not going to be preserved. But the good news is that in our next stage, when we optimize frequency optimization, the equilibrium will be achieved again, and that every step we are taking is going forward in terms of diminishing social costs. So we can assure that we're not going to go back at any stage. The new solution is the one we're showing here. On the last slide, I forgot to tell you that savings, we're showing two kind of savings. The one here that is 0.5% represents how much we're saving against last iteration, and the second one is accumulated savings. So we're going from 8 to 9 on this iteration. Iterating some more times, taking different lines into account, will get us to this final solution. You see that we're using a lot of services. The frequencies are pretty reasonable. We're not using services with low frequencies. The zeros over there on line 3, 5, and 6 is because we wanted to preserve the regular service on the optimization until the last stage, just in case they were needed back again. And finally, we have to point out that our final savings are of 30.2%. That's a very high number. This is how the savings evolved over the iterations. We're not going to stop in this because we're running out of time. So our final solution, this is just to show you how our model was able to generate a solution that looks pretty close to what you see on maps on the streets. We're giving 2 or 3 different services on each direction or on each route. Some of them have regular services, some of them have only express services, but this is obviously just a consequence of the particular demand matrix we used for this example. But the model works on different demand matrices, of course. We have that. We have some publications where we explore when we study the effect of the form of the demand matrix on how big are the benefits of the services we use. We invite you to check them out. So for our conclusions, first of all, we have presented a model that's able to find a solution to the express service design problem, which generates its own services, it's consistent with user equilibrium while minimizing social costs, does not exceed capacity, and finally works on networks. These were our main objectives, and we were able to accomplish them. On the frequency optimization problem, we were able to find new improvements to this model, such as continuity restriction, transfer node limiting. We didn't talk about this due to the time restriction on this presentation, and improvements to the capacity algorithm, and it made the problem easier to solve. But still, the bi-level approach using the network algorithm, we mean separating the passenger assignment to the frequency optimization, could be used in the frequency optimization problem, making it even easier to solve and applicable to larger instances. We also would like to see what happens when we take into account other forms of capacity, such as the maximum capacity of bus stops. That would be a very, very interesting capacity restriction to take into account on heavy demand corridors, because the stop restriction is binding in some of these cases. We also would like to see what happens if we take other user behavior assumptions into account. We're currently working with route optimization, but users could be optimizing the strategies as well. On the service generation problem, we found different ways to generate services to feed the frequency problem, yielding savings around 10%. Furthermore, we found some cases where the problem can be solved in optimality in presence of congestion, which opens new possibilities. However, we think that numerical solutions could improve the generation formulas by avoiding approximations. The formulas we showed, in order to be able to show explicit solutions and simple indicators to be able to use, had to go to some steps where we made some slight approximations. We could alternatively solve them numerically to see what we get. We think that it's not going to make a big change, but it would be worth trying anyway. We could also study different service configurations besides zonal and short-term services. And finally, the results for the generation heuristic could be tested against the services that an expert would design. We want to make a little experiment when we give a scenario to an expert and we tell him what express services would you provide in this particular situation, and then test those services against the ones we design. Finally, on the network express service design problem, we saw that our model is able to generate and optimize the service over a corridor, which can carry benefits as high as 30% cost reduction. But still, the route selection problem at the beginning can be improved and automated. The model has not still been tested on large networks. However, the bottleneck of the algorithm occurs in the frequency optimization problem, which can take instances of larger sizes than the ones we've tried. And we also have this bi-level approach idea that we think that will allow us to face even larger scenarios. Finally, a computational tool is in our future plans. We want to develop this model as a software. So, thanks for your attention. We're going to take some questions, but before that, we would like to invite you to the next webinar that's titled Traffic Safety on Bus Corridors, and it's going to be presented by Nikolai Duduta from Embark on Friday, 27th of September, and you can go register on the address on the website over there. So let's take a look at the questions. I can see there are no questions right now. Let's give you a minute to give me your questions. No questions. Here's a question. Stefan Steiniger is asking, how was it implemented so far? Well, the different stages have been implemented different ways. The first stage, the frequency optimization problem, was programmed in AMPL using the minus solver. We also had to make that interact with C++. and we were able to make this small software that could deal with small corridors, because it uses the old version of Leiba's algorithm. The service generation program was we made a new version of the frequency solver using the same tools I mentioned before, minus AMPL, and we made a program on AMPL that was able to solve the problem for larger networks, for larger corridors. I'm sorry, corridors with up to 40 stops. And on the final stage, the network design stage, we haven't been able yet to program it properly, but we solved the iterations manually using the tools I mentioned before. We solved the corridor problem using the code we have already made, but the iterations, the transfer of information between stages was done manually. And well, by implementation on the real world, on real buses, we're on our first stages so far, but we have studied some real case scenarios such as Avenida Grecia in Santiago, and we also have been in conversation with the people from Brazil. We're taking a look at the current solution for the Trans-Brazil corridor, and we're using our model to evaluate their solution and to try to design new services. But mainly we're using our model on this stage for this really big real case scenario to be able to evaluate the solutions. I hope that's what you wanted to know. Feel free to reply with a different question. We have another question from Gail Wooton. He asks, how could you adapt the model to vary service provision at different times of the day? That's an interesting question. I didn't talk about some basic assumptions of the model. I forgot mentioning that we're assuming that we're working on a fixed demand matrix. I guess you took that from context anyway, and that this fixed matrix represents the operation of peak hour, peak time of the day, and the adaptation for different times of the day would be assuming that you know that you have a fixed matrix for different times of the day, and you fit those different matrices for the model. But the practical concerns of how to make the transition from one time of the day to the other time of the day, or I guess you wouldn't want to have different services, completely different services operating at different times of the day. I guess that the most reasonable way to deal with that is to design services for the peak hour of the day, the critical time of the day, and then feeding those models without generating new models for the rest of the times of the day, of the periods of the day. I'm going to take another question from Francisco Lopez Ramos. Do you take into account fleet size in the frequency optimization model? The short answer, yes. The detailed answer, we're not taking fleet size explicitly as a restriction, because fleet size is part of the social costs. A bigger fleet size means bigger operator cost. So the social cost will find the balance between fleet size and frequency. Any more questions? Or here, Stefan. You think that all proposed new routes are feasible? I see a problem in particular that users will understand the different stop options. Yes, I think this is an issue that we will have to face at some point. But I think the tool we're developing gives the input to the people that are going to have to take this particular decision. I don't see how we can take these kind of concerns into account on a model. I think that the person that uses the model is the one uh, that has to use the tool properly to deal with this. But I would like to know what you mean by the particular problems here. Understanding the different stop options here, I can show you again. I don't know if you're seeing if you're what are you seeing in my screen. I think you're seeing like PowerPoint but not full screen, right? All right, good example. Stefan is pointing out that he means things like red line versus green line in Santiago. I guess that what he's trying to say that in Santiago we're trying to, in the metro of Santiago, for the ones that don't know, we have two on peak period of the day. We have two services running on the same line with no overtaking. They are called the red and green line, and they skip some alternated stops so the trains can go faster. Of course, they have some shared stations, and they hence are able to have a shorter cycle time and give and improve capacity. So I guess what he's trying to say is that to be easier to understand, we have to keep our design simple. But the solution I showed you, the example I showed you, um, may look a little complicated at first sight, but if you take a closer look, I will use the pen tool here. If you take a closer look, you will see that, for instance, on let me see, am I drawing on the thing or no, I'm not. Yeah, here's a pen. If we take this route, the one that goes that way, we will see that we only are giving 3 services on one direction and 2 services on the opposite direction. And I would say that this particular route is the most complex one of the ones we design. But I guess it's fair to acknowledge that this is not the solution the model gave us per se. We had to take the solution and make the changes that we felt were necessary to obtain a reasonable solution. But the model was able to lead us to that solution. We took an initial solution that had many routes, well, not that many, but many services, and then we forced that solution to leave out some of the services and just work with the services that really made sense in terms of minimal frequencies, or we took out services that were really similar to each other. You don't want to give 2 services that have just one stop differentiating them. So those kind of issues were solved by hand, we could say. Yeah. Well, let me see if we have more questions. Yes, we have a new question from Francisco Lopez Ramos. He says, just if you can clarify me, the inputs to the design of services algorithm include the only frequencies computed by the frequency optimization problem or something more. Let me take a minute to understand. The design of services algorithm, yeah, I guess you mean the service generation algorithm. The service generation algorithm does not work with frequencies as an input. It works with a corridor, with a topology, and demand matrix as an input. And with this information, it looks for good services to feed the frequency optimization problem. The particular heuristic I showed you here optimized itself the frequencies for a given zonal service, and if the optimal zonal service in particular that you were studying was good enough, it was fed to the frequency problem. But our heuristic tested every single possible zonal service that was better than not at all, and then the frequency optimization problem choose amongst them which ones are the ones to use on the final solution. Do we have any more questions? I guess we are running out of time. I think I could take one more question if you have anything. So I guess that's all. Thanks for your attention. Thanks for your feedback, and we'll see each other on the next seminar. Yeah, I'm getting thank you too on the questions. So thank you all, and see you soon. Bye.